Problem in fluids, number 1, problem number 3. The pressure in a perfectly cylindrical can of soda was measured by one of the students to be 276 kilopascals. The pressure is due to carbon dioxide in the soda pushing upwards on the lid. The top of the can has a diameter of 6.50 centimeters. If the can is sitting on the desk and the barometric pressure outside pushing down is 1.03 atmospheres, what is the force that the aluminum can exerts on the CLT to keep the container sealed? So we have three things happening. We have the carbon dioxide pushing this way, we have the atmospheric pressure pushing this way, and now we have the metal in the can, which obviously is balancing those two forces. Thus, as a minimum, we have the force produced by the metal plus the atmospheric force must be equal to the force that the soda, the carbon dioxide, pushes up on top. So the soda is pushing this way, atmosphere is pushing this way, and the can must be also pushing down to hold the lid in place. Let's first calculate the area of the top of the can. The area is pi r squared, which is pi. I need the radius, which is 6.50 centimeters divided by 2, but I really need that in meters to get to the SI system, so I have 100 centimeters in a meter, and that entire quantity needs to be squared. That area would then calculate to be 3.32 times 10 to the minus 3 square meters. So the pressure of the can is going to be the force per unit area. That tells me that the force of the can is going to be the pressure times the area. So here's the force of the can equal to 276 kilopascals, but that's 2.76 times 10 to the 5th newtons per square meter. I multiply that times the area of 3.32 times 10 to the minus 3 square meters and get 916.3 newtons. We've calculated now the force that the soda produces pushing up on the top of the can. We now need to calculate how much force is the atmosphere putting on it. Well, we know the atmospheric pressure is also force per unit area from the definition of pressure. So therefore, the force of the atmosphere is the pressure times the area. In this case, it's 1.03 atmospheres. And we know that an atmosphere is 101.3 times 10 cubed pascals, which would be newtons per square meter. And we calculated the area already to be 3.32 times 10 to the minus 3 square meters. That gives the atmospheric pressure pushing down a force of 346.5 newtons. But the metal in the can is obviously holding the two together, so I have a force pushing down of 346.5 newtons. I have the soda in the can pushing up on the inside, the carbon dioxide, with 916.3 newtons. So the metal in the can has to at least produce the difference between that. So the force in the can, or the metal here, is 916.3 newtons minus 346.5 newtons, and so the can must at least be exerting the metal in it 576 newtons of force.